Magnets, it turns out, are dipolar. So in the same way that charges had two types of charge, positive and negative, magnets have two types of poles, and they are called what you think they're called because we use them in geography as well. North and south. And I apologize in advance to those of you trying to learn this from YouTube. I'm going to be doing a lot of gesticulating and gesturing, and you can't see that. Just live with it. If this was a bar magnet, for example, that might be the South Pole, that might be the North Pole. And because electricity and magnetism are two different sides of the same coin, in the same way that like charges, like poles repel, unlike poles attract. You may have tried to push two magnets together and found that they were repelling each other. It was because you were trying to push a north against a north or a south against a south. However, unlike electric charges, it's impossible to completely isolate a north pole or a south pole. Electric charges, the smallest negative charge was an electron. The smallest positive charge was a proton, pretending quarks don't exist. You can isolate a positive and a negative charge. We call that the elementary charge. Magnets don't work that way. If I were to break this magnet in half by snapping it, that would end up being a south pole. That would end up being a north pole. I would get two small magnets that each still has two poles. Magnets send out invisible but detectable magnetic field lines. And we have the same problem as we had with electric field. With gravity, Jacob, everything fell one direction. But with electricity, we said that like charges, and so we had to define the direction of electric field. Which way would a positive want to move it could? Like poles, we have to define the direction of magnetic field. And we chose to define it this way. All magnetic field lines point from north to south. Or sometimes you'll see it expressed in terms of a compass, the direction a compass points. Compasses point south. Mr. Dueck, wait a minute. I don't mean to argue with you, but I've seen a compass. My compass points north. No, it points south. Mr. Dueck, I'm sorry, but I was in Boy Scouts or Girl Guides. I'm pretty sure my compass points north. No, it points geographic north. But do you know what magnetic pole is underneath the geographic north? A south magnetic pole. And it's going to get really confusing, unfortunately, because map makers refer to that south magnetic pole that's underneath the north geographic pole as magnetic north. They should have called it magnetic south, but they didn't know what they were doing. We'll talk about that. What was our symbol for electric field? Capital E. What was our symbol for gravitational field? Lowercase g. What would our symbol for magnetic field be? Why can't we use M? Taken. Why can't we use F? Uppercase is force, lowercase is frequency. So we're going to pull out from a Latin word. The abbrev for magnetic field is going to be a capital B, and it is a vector. You'll hear me talk about a B field. That's a magnetic field. And Caden, you get to learn a brand new unit today. Magnetic field strength is measured. What was electric field? Newtons per coulomb. What was gravitational field? Newtons per kilogram. Magnetic field is measured in Teslas. Abbrev, capital T. You will also, there is another SI unit for measuring magnetic field strength. That's Gauss. And so you'll sometimes see that. We're not going to use that. We're going to use Teslas. Earth's magnetic field, there's some variation, but it's around on the order of 10 to the negative 4 or negative 5 Teslas. That's enough to move a compass needle. A very strong magnetic field, 1 Tesla is very strong. If I gave you 2 1 Tesla magnets and I said, here's $100,000 to pull them apart, I'm keeping my $100,000. Not a problem. If you're doing it with human strength. In fact, put your pencils down. I found this on YouTube a few years ago. This is late at night in a hospital. This is a 4 Tesla MRI machine. Where is it, Mr. Dueck? What did I call this one? Metal objects, not metal. Okay, got to remember what I called it. Metal objects inside. So MRI machines, the M stands for magnetic. They have very strong magnets, and this always works better when the video opens faster. Did it this morning too. It just took its sweet time. There we go.
Whoa!
Not a problem if your head is there, because there's very little metal in your head, despite what your mom says to you sometimes.
So the force we're reading on that guy right now, just at that part of the magnet, is...
How many pounds? Pretty much 300 pounds.
Close to 300, 280.
And you'll see on the other end, we're suspending a wrench in midair. It's just hanging there being pulled. This is why, for a 4 Tesla magnet, this is why I said to you, none of you are going to pull apart a 1 Tesla magnet.
Okay.
In fact, it isn't quite dead center. It's a little bit off, and so you're going to see suddenly as it's drifting sideways,
now.
it's going to clamp to the wall.
It's going to attach itself to the board here in a second.
Any second, it's going to start dropping, yeah. Gravity will just do enough.
There it goes.
There it goes. Oh, that's all
And now, it is giving us a reading of...
In other words, for you to pull that wrench out, you'd have to be able to lift 500 pounds. None of you are pulling that wrench out. You're not.
500.
500 pounds. Whew.
Hey, what would it do to an office chair? Good question. And right around now, I do my public service announcement. If you are ever in an MRI machine, if you have any piercings that you're embarrassed about, tell the technician and remove them. Otherwise, they're going to get removed for you in the most painful way you can imagine. Here's an office chair. Doesn't have much metal, but it's got enough to be attracted by this magnet. Wait for it. So just there,
50, 560.
what do we have for force?
Whoa. Ooh. We are at 700.
700 pounds of force?
Yeah.
Are office chairs meant to take 700 pounds of force? This one's gonna, it's a trooper. It's gonna try.
700 pounds.
Oh, it's about
Oh, whoa. And we have jumped to 1300.
that's exactly what I'm about.
Yeah, we have
Well, the
jumped.
most magnetic stuff is right here, still on top of the chair.
Whoa.
So we're just about to hit the sweet spot.
The
Keep going.
wheel is sitting.
Whoa.
Baby!
There we go.
Oh my god.
What do we got now? No, look at it, 1700 pounds.
We are at 1700, which is far more than this thing.
You just relaxing it now?
Yeah.
Okay, so there it goes. Oh, 1800.
1800.
It's past 2000.
Close to 2,000 pounds of force. So 1 Tesla is very large for a magnet. I have a video, I may get to it another day. The largest magnet that has been made, I think, is on the order of 40 Teslas. The problem is it's strong enough that it also instantly wrecks the camera. I've got a very short video of it, and then all of the magnetic stuff going on inside the camera goes cuckoo for Cocoa Puffs. Yes? It's a great question. It turns out there are 2 main types of magnets. There are permanent magnets. Those are made out of ferromagnetic materials, like those rare earth magnets I brought out earlier. but there are also electromagnets. That's what the MRI machine has. An electromagnet is a magnetic field caused by current. These are really, really useful because it gives us a magnet that we can turn on and off. Oh, and we can control the strength of, because we can control current, because we've just done circuitry, add more resistors, change the voltage. You can customize whatever current you want running through that electromagnet. So if you've ever seen, for example, a video of those cranes that magnetically pick up junky cars and move them around, that round circular thing, it's something called a solenoid. We'll talk about that a bit later in the lesson. It's an electromagnet. It's an electromagnet. I forgot to bring out a couple of toys. I have to pause the video. So what do magnetic field lines look like around a single magnet? Well, magnetic field lines point from north to south. So you can see all of these arrows are pointing from north to south. Now, magnetic field lines have no beginning and no ending. So if I follow this one, first of all, a compass would point that way right there. Don't write this down. A compass right here would point that way. A compass right here would point that way. A compass will point in the direction of the magnetic field. These magnetic fields, when they hit the South Pole, they continue through the magnet and come out the other end. They're I can't say circular. They're not circular. They're not circles, but they're continuous. So magnetic field lines all point from north to south. Magnetic field lines have no beginning and no ending. They continue through the object. Okay. Earth is also a magnet, which is how a compass works. At the north geographic pole, what does the magnet inside the Earth look like? I'm telling you, it looks like that. But it's confusing. If you take a navigation course, if you take a boating course, first of all, the magnetic pole doesn't quite line up with the geographic North Pole. They're off. Right now, the magnetic pole is in Canada. It's slowly moving its way towards Russia because the inside of the Earth isn't static. There's stuff moving there. But there's an offset. If you get a chart, a map, you'll actually see they'll have a compass rose and they'll tell you the magnetic offset at that latitude. And they'll call up there magnetic north. They should have called it magnetic south. And I know why they didn't. They don't want to get into the weeds with people who don't have the physics background, but I'm telling you, it's a south magnetic pole by the north geographic pole. By magnetic north is a south magnetic pole. You need to know this, not the rest of that. So if I were to draw in magnetic field lines, here I have two norths facing each other. Jesse, like poles. So if I drew a magnetic field line, it would get repelled, it would vanish, and because it has no beginning and no ending, it would come to the other end, probably over there somewhere. I might have another line that would leave like that and come like that. From the other magnet, I might have a line go like this, come like this, go like this, come like this. Don't worry, everyone drops stuff. Oh, keep those magnets away from your phones. In other words, don't drop it on your phone. It might mess up with some of the magnetic circuitry inside. They're pretty strong. We are going to be doing three-dimensional pictures on a flat piece of paper. Nuji, how do we do that? We're going to invent some symbols. So an arrow pointing to the left is going to be left. An arrow pointing to the right is going to mean to the right. An arrow pointing up the page is going to mean up the page. An arrow pointing down the page is going to mean down the page. But we're also going to need to show occasionally into the page and out of the page. How do we do that? So here's some symbols. We're going to use this symbol here, a circle with an X. That's meant to be the tail feathers of an arrow going away from us into the page. That's going to be our symbol for into the page, whether it's magnetic field or current or whatever. Now, when I'm typing these up, to do a graphic with a circle and an X in the middle of it is a pain. And so sometimes you may see that I'm lazy and I just do a bunch of capital X's. That's meant to indicate into the page. But if we're handwriting, that's into the page. To show out of the page, we're going to use a circle with a dot. That's meant to be the tip of an arrow coming out of the page towards us. And also, Nuji, because this is really tough to type, sometimes I may just resort to a whole bunch of periods in the background, and you'll say, oh, that's a magnetic field coming out of the page. Let's talk about electromagnets. It turns out if you have a wire and it's carrying current, it will generate a magnetic field. A compass near a wire will be deflected if the wire is carrying current. Put your pencils down and look out. What direction is the magnetic field caused by a single wire? We have something called a right-hand rule. In fact, we're going to be learning 3 of them. Who are my lefties in this? Who's left-handed here? Just the 3 of us? This is one of the few times we have an advantage because we can use the right-hand rule with our right hand while still writing down our answer. Everyone else is going to have to put their pen or pencil down, do the rule, remember the answer, and then write it down. So, finally, for once, the world is in our favor. Right-hand rule number 1. This is often called Ampere's rule. You point the thumb of your right hand in the direction of the current. Your fingers curl in the direction of the magnetic field. Say what? Everybody look up. Sorry for those of you on YouTube. Here's my current carrying wire. Let's pretend it's carrying a current that way. I would point my right thumb in that direction. Above the wire, the magnetic field will be pointing towards the back of the room. See my fingers? Close to you folks, the magnetic field will be pointing downwards. Underneath the wire, the magnetic field will be pointing towards the front of the room. And, let's do that. On this side of the wire, the magnetic field will be pointing straight up. If the wire was in this orientation and the current was going down, that's your right, on the right side of the wire, the magnetic field, a compass would point towards you. Closest to you, a compass would point to your left. On this side, a compass would point to the front of the room. And on this side, the compass would point that way. You're going to get kind of yoga-ish. If it's really bad, you could probably do the same thing by sticking your hand behind you and doing the same orientation. You'll find that often works. Or sticking your hand down here, but we'll talk about all that. So, this is rule number 1. Example 2 says, sketch the magnetic field, and it says, that's a wire. Okay. What do you think that X means? Into the page or out of the page? What's into the page? I think in this case, it's got to be the current. So here's my suggestion. Until you get good at this, everybody hold your paper up so it's vertical and like my board, so that we're all doing this. What you're going to do is you're going to point your right thumb into the page. Now, I'm going to find it easier to hold my right thumb out here into the page. And I can sketch the magnetic field. It looks like it's going, you know what? I think the direction of the magnetic field, if I draw a little circle, on the left, it's up. Above, it's to the right. On the right, it's down. And below, it's to the left. Is that right? Yeah, that works. No. No? Yes? Okay. Don't quit on me. Follow along and you'll be okay. It's going to be a little confusing. We'll get it. I have an app, actually. Magnetic field of a current carrying wire. So it's going to be under M. There it is. Magnetic field of current carrying wire. Come on, you ran last time. Here you go. So here is a wire with the current moving up. By the way, you'll notice it even shows the electrons moving down because that's what's happening in real life. But the arrow, the current is pointing up. If you point, all of you, your right thumbs up, see how your fingers align with the direction of the arrows. If I pick up this compass and I move it around, It's showing the direction, the red point is showing the direction of the magnetic field. As I get closer, the magnetic field gets stronger. As I get further away from the wire, the magnetic field gets weaker. What would happen if I flip the current? Well, point your right thumbs downwards, all of you. Yeah. Now the magnetic field goes in that direction. Okay? Example 3. It says, which way must the current flow in the wire below? What are those dots and X's then? That's the magnetic field. So pretend you're holding that wire. You may find it easier to hold your paper vertical. With your right hand, hold that wire in such a way so that above the wire, oh, what do those dots mean above the wire? What direction is the magnetic field? Out of the page. What do those X's mean underneath? So hold your right hand, it's either going to be this way or this way, in such a way, because you're going to point your thumb along the direction of the current, so that your fingers curl in that direction. I'm not going to look at any of you. You can see if you can try and figure this out. I'm going to do it the correct way in my pocket, and this way, yes? It's got to be thumb pointing to the right. That curls. Now, some of you may, especially righties, you may find it easier to have a wire analog, like a pen or a pencil. That's where the wire that I'm holding is. And yeah, above the wire, my fingers are pointing towards me. Beneath the wire, my fingers are pointing away from me. The current in this wire would definitely be moving to the right. Now, current we defined as which way positive protons would move. What if we're dealing with electrons? And we will be dealing with electrons because in particle accelerators, it's much easier to get a beam of electrons. Well, if you're dealing with electrons, you got two options. You can memorize a whole new set of left-hand rules. Meh. Or an electron moving to the right is the same as a proton moving which way? An electron moving down the page is the same as a proton moving. If you give me an electron, I ask which way is it moving? I point my thumb in the opposite direction because that's which way a proton would be moving, and I can still use the same right-hand rule. That right-hand rule also shows up in torque, by the way. When you're using a screwdriver, if you want the screw to go this way, turn the screwdriver this way. If you want the screw to go this way, turn the screwdriver this way. I use that all the time. The whole righty-tighty, lefty-loosey thing never worked well for me because I'm a lefty. I'm often using the screwdriver with my left hand because it's my dominant hand, but I have this one handy. Okay, I want the screw to go this way. I'm going to turn it that way. I can figure it out. So that's built on it. It's a vector cross multiplication, which we'll talk about a bit later. So here is a picture I found online of the right-hand Ampere's rule for a current carrying wire. Now, that's a single wire. What if we got more than one wire? Let's talk about a solenoid. If we wrap a wire around and around and around and around, always going in the same direction, around and around and around and around, you get a whole bunch of overlapping magnetic fields. We call this resulting coil of wires a solenoid. Here's a couple of solenoids. This one here is a really big one, so you can just see the concept. Transparent. This one is a far better one. There's way more wires packed closely together. The closer you can pack the wires together, the stronger the electromagnet effect that you'll get. So you'll find some solenoids where the wires are unbelievably packed together. I've got one about yay big at home in a Tesla coil, and I think it's 1 million turns of wire in that stretch. They really cram them close together. Caden, here's the question. What will the direction of those overlapping magnetic fields from all of those wires wrapped around be? Let's figure that out. So here's a typical solenoid. Turn the page. We learned early on, Tony, that we can dramatically increase the strength of the magnetic field by putting an iron core in the center. In other words, I took the object that I took this from, there was actually a piece of iron, a square piece of iron that fits in there, because now the iron also becomes magnetized. When you turn a current on, you get a really strong magnet. That's why those car cranes that pick up junk cars, those cranes, look at the magnets on the end. They're circular. They're really, really strong solenoids. They're wrapped around a central coil. We call this an electromagnet because it's a magnet that you control with electricity, hence your question earlier. You would shut off the electromagnet. Now the magnetic field is zero and you can get stuff out of the MRI machine. And it has, honestly, I don't think I'm exaggerating. It has millions of uses. They're used all over the place. So, how do you figure out the direction of the magnetic field from a solenoid? First of all, you'll be given a picture of a solenoid, so you'll know to use this rule. This is right-hand rule number 2, the right-hand solenoid rule. You imagine that you're holding the solenoid in your hand. Here's my solenoid analog, this round tube. You imagine you're holding it in your hand. I can hold this in one of 2 ways. Sorry again for those of you on YouTube. I can hold it like this, or I can hold it overhand like this. Those are the only 2 ways that I can hold it. You curl your fingers in the direction of the current that's going through the wires. Your thumb points north. Your thumb points north. Okay? So, curl your right hand fingers in the direction of the current. Your thumb marks the north end of the electromagnet. We'll do one in just a second. Example 4 says, what direction is the magnetic field below? I didn't give you a solenoid on purpose. I just gave you a rectangle because I wanted to show you how you can draw a solenoid to make it look 3D-ish. So everybody put your pencils down and just look up for a second. Tony, you too. Thank you. To make a solenoid look 3D-ish, you use stretched out letter S's or reverse letter S's. Watch, if I want to make this look 3D-ish, I'll go like this. Here's my battery. I'll have the current going like this, and then I'll go and you can see you get kind of a 3D effect where your brain says, oh yeah, I see what's going on. So I used stretched out letter S's. If I'd wanted things to look different, I could have reversed the S's as well, which is what I did this morning lesson. Copy that out. Have the battery going that way. Have the first wire go over the top in front. Have it duck behind, and then do a bunch of long letter S's to make yourself a solenoid. Draw that. And then once you've drawn that, see if you can figure out the direction. If not, I'll do it with you in just a few seconds. Okay? Presley, the very first thing I would do is label downhill. Current, current. It ducks behind. You know what? I think the current is running this way through these wires. So the only way that I can hold the solenoid like this or like this. Which one of those will have my fingers align with the direction of the current? Yeah, my thumb's going to point to the left, Caden, not to the right. Yes? Get your right hand out and try it. You can't be passive in this. Okay? So I'm going to say this must be the North Pole. This must be the South Pole. Now, that's outside the magnet. If I draw this magnetic field line, inside the magnet, it would actually point from south to north. We had to pick a direction somewhere, and so we said, we'll talk about outside the magnet. Thank you very much. It's just limits to what we can do because they don't end. So this is the solenoid rule. This is the direction of all of the overlapping magnetic fields from those individual wires going in circles. We use solenoids in transformers, not the toys, the electrical devices. Motors, generators, television, speakers, doorbells, fire alarm bells, cell phones, power door locks, etc., 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 etc. Let me just give you one example that you didn't maybe realize. Our fire alarm bells. My friend used to live in a building that was built in the 1930s. Yeah, that long ago. And this was their fire alarm bell. Old style. Here it is. I had to take a picture. This right here, Ella, is the solenoid. It's plugged in. Now, this is running alternating current. So what would alternating current do? You would have a magnetic field going this way, then this way, then this way, then this. You would have right here, north, south, north, south, north, south, north, south, north, south, an oscillating magnetic field. You glue a magnet onto the end of the clapper, and it'll get attracted, repelled, attracted, repelled, attracted, repelled, attracted, repelled, attracted, repelled. Ding, 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 ding. Our bells still work the same way. All they've done is to prevent vandalism, they put the bell infrastructure over top of this. Now this is inside there, so people can't vandalize it. But I'm telling you, that's how the alarm bells work. It's so simple, it's analog, very few moving parts, and it'll work. As long as magnets still work, they'll work. The old style phone ringers that you hear in old TV, the ones that actually made a dring sound. There was a solenoid. I used to have a phone back there that I'd taken apart. I think I've finally recycled the parts, but there was a lovely solenoid in there. It was an alternating current. That was what was ringing the bell. Power door locks. The new ones are a bit more complicated, but the original power door locks that went up and down in the old 1970s cars, it was a solenoid. You ran the current through this way, it attracted. You ran the current through this way, it repelled. That got your lock up and down. They're used all over the place. I guarantee the vibrating mechanism of your phone, there's probably there's a solenoid being fed an alternating current causing something to vibrate back and forth. Very handy device. Example 5. In figure 7.9, the conductor on the left carries current into the page. Does that make sense? So I guess we're looking down a wire. This is not a solenoid. The conductor on the right carries current out of the page. Yeah, that makes sense. That's the symbol for out of the page. A says, draw sample lines of force around each conductor showing their direction. So, Jacob, this is not going to be the solenoid here. It's going to be the first one. Again, if you don't like your orientation, feel free to hold your paper vertically. I'll do it up here. I'll do the left-hand wire. I would point my right thumb into the page, and you know what? The magnetic field lines are going to go in this direction. I'll draw a circle. The magnetic field lines are going to go that way, that way, that way, that way. The second wire is coming out of the page. Oh, okay, I can see that. That way, that way, that way, that way. Is that okay? Here's what I want you to notice, Presley. Right here, where the fields overlap, are they like or unlike? Be stupid obvious. Like fields, these wires will actually get pushed apart, and electricians have to take that into account. If you ever see an electrical wiring system, you'll notice every very short distances, they re-secure the wires with staples if it's wood or with glue. That's because they know if you have sets of wires running next to each other, they will be applying forces on each other, either attracting or repelling. And if it's something you're switching off and on all the time, that means those wires would be feeling a force. They might slowly wiggle loose, and loose wires fire bad. So if you ever do wiring, you'll see the recommendations are every so often secure the wire, every so often secure the wire. You don't just let it loose and kind of hope for the best. Okay? So it says, would these wires attract each other or repel each other? They would repel each other. If we had two wires carrying current in the same direction, they would attract each other. Which is a bit of a pain for electricians, but wait a minute. With a bit of cleverness, maybe we can turn that into some type of useful motion. Let's put that in our back pocket. Oh, here's a solenoid. The first thing I would do is I would label downhill. Oh, someone's done that already. What side is going to be north? Don't blurt out your answer. And this time, I'm not going to hold my hand up. See if you can figure out. Imagine holding the solenoid in your hand. Will A or will B be north. You can't do this passively. So if you're trying to do it under your table, Nuji, I'm not going to let you get your hand out and in front of you. Jacob, I'm looking at you too, unless you've done it already. Okay? And Nuji, can I give you a little bit of advice? Doing it, you're going to get it wrong. Get your hand out in front of you. Trust me. When I first started teaching Physics 12, my first year, there was still a provincial exam. And the kids were all writing in the library. About halfway through the exam, my phone rang, and the teacher that was supervising, oh, Mr. Dueck, you're going to be so disappointed in your students. They're giving each other hand signals. They're communicating answers from the multiple choice section. So I learned, I said, no, they've got to the magnetic section of the test. So I learned every year after that, I would say to the teacher, about 45 minutes into the exam, you're going to have these kids doing all this weird stuff. They're not giving each other hand signals. It's a right-hand rule. But I'll tell you the same thing my physics prof told me. You want to get this wrong? You want to get this right? Get your hands out wide. It's way easier to visualize. A or B? Which side's north? I agree. Now, remember, what that really means is this. Outside, north is on the right, which means the magnetic field below is actually pointing to the left. Inside, the magnetic field is pointing to the right. The magnetic field above is pointing to the left. I can make the same argument. But inside the solenoid, the magnetic field is pointing to the right. By the way, Joseph, you're also seeing why an MRI is shaped like a tube. You're laying inside one mother of a solenoid, a very strong one, with many, many turns of wire, and also running a huge current. So we have the right-hand rule, Ampere's rule for a single wire. We have the hold the solenoid rule. The third one is the trickiest one. It's called the right-hand motor rule. Spoiler alert, it explains how electric motors work. That's why it's called the motor rule. Suppose we have a single wire carrying current through an external magnetic field. So here's my wire. There's current. But it's passing through a magnetic field. What direction is the magnetic field? What are those dots meant to indicate that I hastily drew? Out of the page, okay? And we'll say into the page or out of the page when referring to the dots and X's. Okay. This wire, because it has its own magnetic field, will interact with the external magnetic field that's going through. This wire will feel a force. What direction? Presley, this is the confusing one, okay? To find the direction, what you want to do for this one, and you'll recognize it because there's a current carrying wire, there's an external magnetic field. That's how you recognize it. First of all, you want to have your hand in hitchhiker high five. Okay? Thumb up, palm flat. Not like this, not like this. Okay? Here's the rule. You point your thumb, right thumb, in the direction of the current. You point your fingers in the direction of the magnetic field, which for me is out of the page. Your palm pushes in the direction of the force. This wire will feel a force down the page. Now, I'm kind of getting a little contorting like this, and so if I'm having a tough time, I realize, oh, why don't I do that behind me? There, now my thumb is still pointing in the direction of the magnetic field, of the current. My fingers are still pointing in the direction of the magnetic field. My palm pushes down. In other words, at the bottom of the page, we can write down the page. What we're doing is actually vector multiplication. There's two ways to multiply vectors. One is a dot product. That's when you use the dot as a times, and you get a scalar answer. Work is not force times distance. Work is force dot distance. Gives you a scalar answer. The second way, you use the times sign. We call it a cross product, and you get a vector three-dimensional answer. Look up. That way, cross that way is that way. Sorry for those of you on YouTube. That way, cross this way is that way. Your right hand has a built-in cross product multiplier for you. Up, cross to the back of the room is to your right. Right, cross up the room is to the front of the room. That's the right-hand motor rule. It shows up in other physics applications as well, but that's the right-hand motor rule. It's a cross product, just saying. Whew, we're going to practice this like cray-cray for the rest of class. Example 7 says, find the direction of the net force on the wire. Okay. I point my thumb in the direction of the current. What direction is the current in this picture? No. Because what's the arrows to the left labeled? B field. That's the magnetic field. There's the wire. What does the X mean? So if we're using this, if you want to hold your paper vertical to match mine, I would point my hand into the page. My fingers go in the direction of the field. You know what? It's going to be easier if I shoot my hand across like that. Otherwise, I'm having to bend weird. My palm pushes. Which way will this wire feel a force? Up the page. The only stupid thing I have to help you remember is palm pushes. The problem is field and force and fingers all begin with the letter F. Your fingers go in the field, but your palm pushes the force. Oh, thumb's the current. I got nothing for that. Up the page. Put your pencils down, look up. This is from MIT. Jumping wire. So here's their setup. It's a pretty substantial force. We've got a 12-volt car battery, on-off switch, wire, and then a pretty strong magnet. So watch what happens when you turn on the current. Throw the switch and what direction was the force? Starts with letter U. So again. What's going to happen if we reverse the current? Oh, it's still up. Reverse it. I have my own little version of that. I'm going to need a volunteer. Practice these 3 right-hand rules. I like number 8. I like number 8. Number 8 is a nice question. An electron is traveling to the right, enters a magnetic field as shown. Which rule is this one? There's an external magnetic field that we're entering. This is the 3rd one. Except we got a problem. Our rule doesn't work for electrons. An electron traveling to the right is the same as a proton traveling which way? Everybody point your right thumbs to the left, please. And this is going to be the hi-fi hitchhiker one. What direction is that magnetic field? What do those X's mean? Tail feathers of an arrow into the page. Which way will this electron feel a force? Down the page. If you happen to have, growing up, an old-style CRT, cathode ray tube, television, those were the ones that had the slightly curved screen from the side, and when you looked at the back, there was that big thing sticking out the back. If you had one of those, all that was back here was an electron gun. It was firing electrons at the screen, which meant if you brought a magnet close to it, you got some interesting effects. Put your pencils down, look up. So here's an old-style cathode ray tube television. I think you still had those when you were kids. By the way, very basic technology, how TV worked from the 1930s. I hope to fit it into a lesson, but we'll see. Flat screen, modern screens, very different, very cool. But if you bring a magnet nearby, it'll deflect the electrons. Don't do this to your modern TVs. Probably determine how damaged. parts of them. I think you will deflect them too, but you might not be able to reverse the angle. How do you get a black spot in the middle? No electrons are hitting there. The electrons are being deflected so much. On the old style TVs, the inside of the screen was coated with a phosphorescent paint that would glow when an electron hit it. Very low tech. It worked great. No electrons are hitting there, no glow. Example 9. Okay. This, I think, is not a current carrying wire. This is not a solenoid. This is the third one. We have an external magnetic field. But the first thing I need to do, and I would encourage all of you to do this, is draw in the magnetic field lines, because they're not in the picture. Magnetic field lines point from what to what? I usually draw 2, and that's enough for me to figure out. This is a bit tricky because it's a three-dimensional picture on a flat piece of paper, but it looks like this proton is moving into the page. So I would point my right thumb into the page, and oh, magnetic field line is pointing to the right. Which way will this proton get deflected? What's the correct answer? A, B, C, or D? Read carefully. What's the correct answer? A, B, C, or D? What do we think? B, toward the bottom of the page. Yeah, and yeah, it's up to you. If you want to hold your paper vertically to match my orientation, you can. As you get good at this, you won't need to. But starting out, oh, here's very similar. I'm going to draw in the magnetic field lines from north to south. Although this is an electron traveling to the right. Does our right-hand rule work for electrons? No. But wait a minute, Caden. An electron traveling to the right is the same as a proton traveling to the... So I'm going to point my right thumb to the left. Magnetic field. I started to bend like this. And I went, wait a minute. I'm putting a curve in my high five. You know what? I shot my hand down here. That was way easier. Now I can keep my hand straight. And I'm, A, B, C, or D. Which way will that electron get deflected? Again, make sure you don't put a 90-degree bend in your hand. You can bend your wrist, but your hand has to stay like you're giving a high five, right? Sorry. To the right, down the page. No, to the left. Electron traveling to the right. Proton traveling to the left. Magnetic field down the page. I'm getting out of the page. Is that correct? Is it B? Yes. Pause. Have a moment of sympathy for the kids that are absent trying to learn this from YouTube. Not being able to see any of this. Yeah, I know. I warned them. Ooh, number 11. This is not the one we just did. This is the current carrying wire. This is the first right-hand rule that we did. What was that one? Point your thumb in the direction of the current. Your fingers curled in the direction of the magnetic field. What direction is the current in all of these 4 wires? What's that dot mean? Out of the page. So if you're going to use this screen, you would go out of the page. Oh, A, B, C, or D? Gotta be A. I'm pretty sure example 12 is going to be the solenoid rule. How do I know? There's a solenoid. By the way, wait till we have wires inside of solenoids or charges moving through solenoids. Wait till we're combining these. Jacob, it's going to be fun, honest. First thing I'm going to do is I'm going to label the current because I can't follow it. You know what? I think it's pointing upwards on the part that's facing us, yes? Okay. It says, what's the direction of the magnetic field inside the solenoid? We'll do that last. And what's the polarity of the solenoid? Let's do that first. Do the right-hand solenoid rule. Imagine holding the solenoid in your hand. Is the North Pole at X or is the North Pole at Y? Let's see. Why can't I hold the solenoid this way? My fingers are curling the wrong direction. So I would have to hold the solenoid this way. Where is the North Pole, Nuji? At what letter? X or Y? Your thumb points north. Yep. So look up. Yes, no, yes, no. So I can already cross out B. I can already cross out D. Now, that's the North Pole. That's the South Pole. If we draw in the magnetic field line, it's going to go this way, this way, this way. Which way will it be traveling inside the solenoid? From Y to X. No, no, yes, yes. What's the correct answer? Obviously. Yeah. If you haven't figured out those 2-column multiple choice questions, it's a nice way for me to assess a couple of concepts. Read them down, not across. So much easier. Do 1 column at a time. Caden's glancing at the clock. We're getting there. A couple more, we're done. I think this is the 3rd rule. How can I figure it out so fast? Because there's an external magnetic field. I'm going to draw in a couple of magnetic field lines from north to south, from north to south. Okay, and I need to draw in the current from positive, goes through there. I think in the wire section that's in the magnetic field, it's kind of going up and into the page. Okay. How am I going to do that one? If I was doing it here, I would go, okay, I can do it like this, okay. If I was doing it on my paper, let me see. I would go, oh yeah, that works okay. I would probably have to precisely stick my hand out a little bit, but I can orient that with my paper, okay. Right? Is it B, yes? Down, down? Yeah. Two more, we're done. Ooh, this is actually a nice application. In particle accelerators, when they've generated a whole bunch of mystery particles, one of the first things they do to separate them out, they pass them through a magnetic field, because the positives will go one way, the negatives will go another way. We'd sort them out really easily. So it says a beam of positively and negatively charged particles enters the magnetic field as shown. Which one is the positive and which one is the negative path? Let's assume they're positive. So if they're positives, which way are they traveling? To the, starts the letter R?
Right.
What way is the magnetic field? What do those X's mean? Arrow feathers going away from us into the page. So I'm going to go hi-fi hitchhiker, thumb to the right, fingers into the page. Which way will the positives get deflected? Path 1 or path 2? Path 1, right? So I would hustle. You know what? I would probably go like this. Plus and then minus, and then I would go yes, yes, no, no, cross out, no, yes, no, yes, B, gotta be B. The amount of deflection also helps you categorize the particles, because more mass gets deflected less mass gets deflected more. Example 15, I like example 15 because it's a trick question. So here's what I haven't told you. It says this, an electron enters a uniform magnetic field as shown below. So an electron traveling to the right, we would think a proton traveling in that direction. There will be no deflection. The path will be linear. Now, why is that? Charges only feel a deflection when they're cutting across magnetic field lines, not when they're going parallel to them. Cutting across, there would be a deflection, or if it was going at an angle through the magnetic field lines, did I say angle? I'm not going to, but it's actually a pretty trivial thing to figure out the components. I'm not going to do components in this unit, but it's not that hard to figure out. But in this case, the answer is no deflection because it's not cutting across magnetic field lines. And by the way, you could try using your right-hand rule, thumb that way, okay, fingers that way. No, thumb that way. No, fingers that, no, thumb. It just doesn't even work. Unless you stop doing hitchhiker thumb, but I told you it's hi-fi hitchhiker. Your homework is every question. Well, your homework is, let me pause for a second.